Estuaries, characterized as highly dynamical coastal ecosystems, are invaluable not only for their economic significance but also for their biodiversity. Think of estuaries as meeting points where the forces of the ocean, tides, storm surges, and waves mix with inland processes like river runoff, snow melt, and groundwater movement. The intricate interplay between such multiple variables can result in compound events with profound implications for economies, environments, and communities.
Understanding the mechanisms behind compound flooding is vital for prediction and preparedness. But traditional ways of assessing flood risk often miss the full picture by only looking at one thing at a time, thereby restricting us from being fully prepared for floods when they happen. We need to take a step back and look at the bigger picture to better understand and prepare for these challenges. When it comes to evaluating multivariate streams, we need to understand how they are structured and connected. Copulas help us to study these connections, giving us insights into how extreme events relate to each other. Once we have got a handle on these connections, we can start to figure out what they might mean in real-life situations. Defining hazard scenarios help us link the structure of these connections to the potential impact they could have. In contrast to univariate analysis, where critical events are defined by surpassing a specific threshold, the multivariate hazard scenario lacks a singular definition. Moreover, in an n-dimensional framework, these sets collect all dangerous values based on suitable criteria and consequently defines the n-1 iso-hypersurface that generates the dangerous region known as the critical layer. In higher dimensions, this critical layer possesses more of a mathematical than a graphical definition, entailing theoretical and computational challenges.
In this study, we have developed a statistical method to tackle compound flooding hazards. Tested in a pilot case in northern Spain, our approach integrates data from rainfall, river discharge, storm surges, waves, and sea winds. Using a 100-year return period, critical events that compose critical layer are identified. At its core, our method employs a flexible bind copula-based framework, enabling estimations of joint probabilities and return periods within this multivariate context.
Having identified key variables, the Kendall-Stokes correlation coefficient suggests a positive statistical interdependence among the variables. As expected, stronger associations are observed, particularly within the metoceanic variables, with storm surge demonstrating the highest values. Given that the proposed methodology relies on these correlations, we provide empirical evidence supporting the suitability of the R-bind extreme copula model for capturing the stochastic dependence structure. When analyzing safe and hazardous occurrences as well as the most likely events, the KRP scenario presented the lowest design events. However, it's important to emphasize that estimating multivariate design events depends on the specific problem at hand. Furthermore, it offers improvements in terms of computational efficiency and provides insights into the underlying physical processes.
This approach can serve as an effective alternative for addressing high-dimensional problems encompassing not only compound flooding but also other environmental variables.